My name is Jeffrey Hangst. I'm from the University of Aarhus in Denmark. I'm the spokesperson for the alpha experiments at the antiproton decelerator here at CERN. A good way to think of antimatter is as sort of a mirror image of normal matter. For some reason, the universe is made of matter. We don't know why that is, because you could, in principle, make a universe out of antimatter. Antimatter is identical to matter, but has opposite properties. For example, the fundamental particles that make up atoms, protons and neutrons and electrons, they have antimatter equivalents, antiprotons, antineutrons, and positrons. Antiproton has the opposite charge of a proton. A proton is a positive charge, antiproton has a negative charge. The thing is, we have to make antimatter in the laboratory. Nature didn't provide us any. It seems to have disappeared just shortly after the Big Bang. So we have to make it if we want to study it. What alpha does is to work with the simplest anti-atom, anti-hydrogen. Okay, hydrogen is number 1 on the periodic table. Anti-hydrogen is the antimatter equivalent of that. We've been making that anti-atom here at CERN in the antiproton decelerator since 2002, producing it by mixing antiprotons and positrons to make a neutral anti-atom. What's new about alpha is that now we've managed to hold on to those anti-atoms. Normally, when we made them in our previous experiment called Athena, the antimatter would escape and annihilate. Matter and antimatter, when they meet, they make energy, they annihilate. What this experiment does now, and the breakthrough here, is to hold on to the antimatter. We have a magnetic bowl, if you will, a kind of a bottle that holds the neutral anti-hydrogen atoms. And this is the first time that this has been demonstrated. For us, it's about what we call fundamental symmetries in nature. What's the structure of space and time? The CERN, we talk a lot about the standard model of elementary particles and interactions. Part of the theory behind the standard model says that antihydrogen and hydrogen must behave in the same way. This is called the CPT theorem. So we want to test that. We want to, and do it in a different way than we typically do here at CERN. This now becomes an atomic physics experiment. We'll try to use very precise techniques to address antimatter. There were about 40 people from 15 different institutes, from the USA, Canada, Israel, Brazil, Japan, the UK, and Denmark, of course. And our budget is small. The operating budget is a few 100,000 Swiss francs per year. The reason we're at CERN is because we need antiprotons. And the antiprotons come down this pipe from the antiproton decelerator. This machine is unique in the world. There's no other place that you can do low-energy antiproton physics. It must be here at CERN. So all the people who are interested in this are here. This is a big magnet, very similar to the magnet you would see in a hospital for doing an NMR scan. It's used to help to hold the antiprotons and the positrons. In this case, the antiprotons coming from the AD. So they get stored in this magnet, a very high magnetic field, and they get trapped in what we call an ion trap. They're held with because they have a charge. Their electric and magnetic fields to hold them. And they're sort of bouncing around in there in the vacuum. It's a very, very good vacuum because antimatter, of course, cannot come in contact with the matter. So we have our antiprotons there, we store them, and we cool them down. The inside of this device is at about 9 Kelvin, actually. And in Athena, we had a very fancy detector, just like very similar to high-energy physics detectors in Atlas, for example, to see the antiproton and the positron annihilate. That's how you knew that you had made antihydrogen. The way you know that you've done it is you capture some antihydrogen and then release it intentionally. You let it go at a given time and you look for an annihilation. And that's how we detect that this has actually happened, and that's what this article in Nature is about.